Hey girls, it's me. Here are the answers for the 7-3. Once you go through those like normal, fix what you can, and then go ahead and submit them. We're going to start, before we do 7-4, we're going to do some review of algebra. Again, I'm assuming that you've heard this before, but just in case, here's a quickie lesson on how to simplify radicals. Now, there's basically 3 rules for simplifying radicals. There are the 3 bullets right here. Okay. Again, I didn't really decide this. Some of them I think are kind of dumb, but again, they didn't ask me. So radicals are simplified when there are no perfect square factors. Okay, so first of all, if there's none, we need to figure out what are the perfect squares. So we're talking about 1 squared, 2 squared, these are your perfect squares. 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, you get the idea, 10 squared, and so on. Okay? What the heck? All right, so I'm not sure what that's all about, but let's see. Okay, I was going to try and do some. All right, there we go. All right, so for example, if you have the square root of 8, okay, that has a factor of 4 in it. So you're going to take that 8 and factor it to 4 and 2, and then 4 times 2. And this piece is going to go down to 2, and then radical 2 is left over, and that is considered simplified. Okay, there's a basic premise here that you know that radical A times any radical B is radical AB. You can go either way with this. You can split it up and factor it like this, or you can multiply it together and put it like that. Okay, so that's your basic premise. All right, let me give you another example. How about square root of 200? All right, now you know it's pretty big. So you probably think, there's probably a square factor. Yes, 100. So you can do 100 times 2, and then just separate it out. So you get the perfect square by itself. And then 10 radical 2. Okay? And just because it's big doesn't mean it's always going to simplify. For example, let's look at, let's see, 38. Radical 38 is 19 times 2. 19 and 2 are both, neither of which are perfect squares, but they're both prime. So radical 38, we leave it like that. Okay? All right. The second one is no fractions as radicands. Remember, the radicand is the number inside the radical. That's a radicand. All right, so we don't want any fractions in there. So this is not considered simplified because clearly it's a fraction. Okay, so again, premise that you need to know is that if you have a fraction, you can do, you can do division like you can. Okay, come on. It's down here again. All right. Cooperate. Pen here. All right. So that's our premise. We can go either way. We can split it up. Oh boy. Come on. There we go. We can go this way. We can go this way. Either way, whatever way you want to go. All right. So let's try it. Get my blue pen. We're going to split it up like so. Okay. Now, as you can see, both of your radicands are not considered. There's no fraction. 1 is not a fraction. 2 is not a fraction. But now what's happening is these kind of go together. There is a radical in the denominator. Oh boy, here comes my line here. All right, so what we have to do is we have to do what we call rationalizing the denominator to get rid of this radical in the denominator, okay? So here we go. We're going to multiply by the denominator radical 2. Because what that does, I'm just going to ignore that line because sometimes it happens, sometimes it doesn't. What happens is you get a perfect square down there, which is you've created that perfect square. 1 times 2 is 2. Okay, radical 2, square root of 4 is 2. Oh boy. Then there's your answer minus the line. Okay, that's a simplified version of this. It doesn't look simplified, but it is. That's whoever decided that. Okay, what if I do another one? And I'm going to do 3/8. Okay, so that radicand is a fraction. Oh boy. Okay, so we're going to split it up. All right, and we could do 8 to make it a perfect square. Okay, 3 times 8 is 24. 8 times 8, 64. We've just created the perfect square in the denominator, so that takes care of this problem. And then now look at 24. 24 needs to be divided down. Let's say, I know there's a perfect square 4 in there. 6 is just 3 times 2. So here we go. We have a 2 from the radical 4. 6 is good. And 8. Okay. And of course, we have a little fraction. Oh my heavens. What is that? All right. We have a little fraction here. So we're going to divide that out. All right. Get the blue pen back. So we're going to take 1 radical 6 over 4, or radical 6 over 4, the simplified version. Okay? So there's a lot involved. I hope you've seen it before, but so then these two bullets really go together. We've talked about how you get rid of the radical in the denominator. It doesn't always start out like that. For example, we could have just started out like 2 over radical 3. The 2 is not under the radical, but we're still going to take care of it the same way. We're going to multiply by itself. Okay, so straight across multiplication. Radical 9 created the perfect square. That little number is annoying, but 2 radical 3, square root of 9 is 3. Okay, now this fraction is simplified. This 3 and this 3, one's a radical, one's a not, so that is done. We are simplified. Okay? All right, so treat a radical like a variable when adding or subtracting. Okay, so for example, if I have radical 5, let's say it's 2 radical 5 plus 3 radical 5, it's sort of like 2x plus 3x, which means I'm just going to add the, oh my heavens, that line. Come on, go away. That is, oh boy, 5 radical 5, and I'm done with it. Okay? All right. We're not going to, I'm sorry about the line. I'm just going to have to ignore it because it's just going to do what it's going to do. All right, let's say I want to multiply radicals. Okay, so we're going to just basically go back to this. Okay? So 2 radical 5 times 3 radical 5. Okay? So 6, 2 times 3 is 6. All right, let me do this a little better here. I'm basically grouping 2 Oh my gosh, times 3 and radical 5 times radical 5. Okay, 6 radical 25. Radical 5 times radical 25 is 5, so 6 times 5 is 30. And don't forget your calculator can help you out too. And I'm sorry about those black lines. I don't know how to get rid of them. They just kind of do what they need to do. So anyway, here we go. Ready for similarity in right triangles. Okay, so you're going to notice that these triangles in this section are all right, duh, okay? And they also have the same look where they have the altitude drawn to the hypotenuse. So you have a right triangle, okay? And then here's your hypotenuse. Your altitude, remember from chapter 5, is your right angle for, this is your altitude right here. Okay? So that is the look of this whole chapter, the first of this whole section, sorry. This first thing says, yes, we have all right triangles. We have 3 pairs of similar triangles. Now, we're not going to spend a whole lot of time on this because I think there's better theorems that you can deal with here, but here's the general idea. Let's say we have this triangle that's right. Okay. We have, of course, this triangle that's right. Oops, come on. Go away. And then we have the original big blue triangle that's right. Okay. You know enough about right triangles that, scoot them over so you can see them all here, that, get rid of that. That we could write a similarity statement. So we would talk about this angle, and this angle matching up, which means this side, and this side would match. Remember, we talked about the proportions on the similar triangles being a match. Okay? So if we want to do that, we need some letters. So let's talk about A, B, C, which is this one. Okay, let's make this D. So that's D, and that's A, and that's B. Okay, this would be D again, and that's B, and that's C. Okay, so when we put those 3 triangles together, we are going to create a similarity statement. Okay, 1, 2, 3 letters, 1, 2, 3 letters, 1, 2, 3. Okay, let's do these. This is my red one. This is my green. This is blue. All right, so the red triangle, let's get the right angle matched up with the right angle for the green one, and blue one, of course, is B. Okay, remember that's how we do this similarity statement. All right, now this other part gets a little tricky. We have to look for a common angle. All right, so if you trace over here, we want to go back to the original, and remember on ABC and ABD that A is the same. So on the blue and the red, blue, blue, A, red, A. Okay, So we get two matched up. We know which one's the third. All right. Let's look. So this has to be red, D, A, B. Okay. And this has to be B, A, C. So we got that matched up. All right. Now the green and the red, or let's see, I think the blue and the green have a common angle. If you look A, B, C, D, B, C, they have a C in common. So the C over here in blue is going to be the C over here in green, which makes A match up with the green, D, B, C, and there you have your similar statement. Okay, so you just have to match up the two, and the third one just kind of falls into place. We're not going to worry about that. Okay, remember, if you have similar triangles, you take any two and you write sides. Remember, the sides are, here we go, proportional. Okay, on similar triangles. Angles are congruent, just reminder. All right, I like these, the correlates coming up next. Okay, proportions which the means are equal occur frequently in geometry. For any two positive numbers, A and B, notice positive, the geometric mean of A and B is the positive x such that A is to x as x is to B. Notice this mean, that's where the mean spot is the same. So it's x. And then A and B are what we call the extremes. Okay? So if you're talking about the geometric mean of 6 and 15, you'll call it x. So we'll put it in the mean spot. And then we'll put the 6 on the one spot, 15 on the other. Okay? Remember, it doesn't matter. We could put 15 here and 6 here. And we're going to find the geometric mean by cross multiplying 6 times 15. I'm going to have to simplify. So I'm going to factor here 6. Here comes my line. 6 is 2 times 3. 15 is 3 times 5. So here's your 9. So that's a perfect square. And then the leftover is 10, which is not a perfect square and can't be. So that's 3 radical 10 is my exact geometric mean. Okay? You could, if you wanted approximation, you need a calculator to put it in there. Okay? But by and large, we're looking for exact. Okay? So that's how you find the geometric mean. Then the corollaries all have everything to do with this same look. Okay? First of all, let's talk about, this is the hypotenuse. And if you remember, the other two sides are called the legs. All right, so now we're going to take and draw an altitude to the hypotenuse like we talked about at the beginning. This is still the hypotenuse, the whole thing. Okay, this is the altitude drawn to the hypotenuse. We'll just call it the altitude. Okay, this is still leg. This is still a leg. These two parts are called segments of the hypotenuse. Segments of the hypotenuse. Okay, so clearly they're going to equal the hypotenuse, but we're going to talk about those separately. All right, so you need to know the parts. You know the parts of the right triangle when this altitude's drawn, then you can do the corollaries. Remember, corollary is just a theorem, just something you got to remember. Okay, so more than anything, we got to remember the words to the theorem. Okay, the altitude, the length of the altitude of the hypotenuse of a right triangle, so the same look, is the geometric mean of the lengths of the segments of the hypotenuse. So here are the words. The altitude is the geometric mean of the lengths, of course it's a length, so we're just going to worry about segments of the hypotenuse. Okay, so that's the words of this theorem that you got to remember. So if you look, here's your altitude. So see where we put the CD. CD is the geometric mean, so it goes in the mean piece. Come on. All right, and then if it's the geometric mean between the segments of the hypotenuse, look at the segments of the hypotenuse, which is AD and DB. They complete the theorem. Okay? All right, so the second corollary, it looks the same. Again, words, very important. I'm going to underline the important words. The altitude of the hypotenuse of a triangle separates the hypotenuse so that, okay, so that's just setting up the triangle. The length, the leg of the triangle. Let's try this again. The leg of the triangle is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse adjacent to the leg. Okay? So a little bit more words, but you can do it. Okay, so notice we have two legs. AC is a leg. Here's my geometric mean, AC. Okay, the hypotenuse is AB. There's that. All right. The segment of the hypotenuse adjacent to your leg AC is right there. Remember, these were the two adjacent segments of the hypotenuse when we talked about the parts. Okay, so we have another leg. It's called CB. So there's your geometric mean between the hypotenuse again, and this time this segment of the hypotenuse is adjacent to the leg that we're talking about up here. Okay, so again, it's very important that you know the words. Okay, just keep saying them to yourself. All right, because that's how you're going to remember them. Okay, so we got 3 examples here. All right, we're looking for X and Y, of course. Okay, so it looks like this, you get that same look for all 3 examples. Okay, so we are going to set up a proportion. All right. Do we need to write the words, or wait, we'll just, okay. First one, we're going to talk about the altitude is the hypotenuse. Altitude is the geometric mean of the lengths. Okay, so the altitude here is Y. So I'm going to put Y in here. It is the geometric mean of the lengths of the segments of the hypotenuse, which are 4 and 12. Okay, so that's how you find Y. All right, this other one next now starts with the leg. So there's a leg that's X. So I'm going to make the leg the geometric mean. I'm talking about this one. Between the hypotenuse. What's the hypotenuse? This whole thing. So that's 16. And remember, it's the segment of the hypotenuse adjacent to leg X. So that would be 4. Okay. All right. I'm going to go ahead and set them all up, and then we'll go back and solve them on a single page. All right. Over here on the second example, looks like the altitude. I don't know why the yellow is mixing there, but I'm not going to worry about it. The Y is the altitude. Remember, the altitude is the geometric mean between the segments of the hypotenuse, which are 4 and 5. Okay. And then the leg again is X. Between the hypotenuse, 4 plus 5, 9. This is your hypotenuse. And the segment of the hypotenuse adjacent to leg X, which is 4. Okay. One more, it looks like 36 is the altitude. And then remember the leg is the altitude is the geometric mean between the segments of the hypotenuse, which are 6x and x. Okay, going back to single page so we can solve these. Hopefully, okay. So here we go. We're going to cross multiply. Oh my. Go away, yellow. All right, y squared equals 48. Okay, we're going to take the square root to get y squared to y. And then we're going to break down, without the yellow, break down 48. I'm talking about perfect squares. You can start small. You can say, I know 4 goes in there. And I know 12 has to be broken down even more. So I'm going to take the square root of 4, which is 2. And then the 12 is, oh boy, now we got yellow instead of black. 4 times 3, square root of 4 again is 2. And then we get a square root of 3. So 4 radical 3 is the simplified version of y. Okay, had we known it, we could have done 16 times 3. 16 is square root of 16 is 4, and then radical 3. So you can do it slowly, or you can do it quicker if you know the factors. Okay? All right. X squared equals, I know 16 and 4 are perfect squares, so I'm just going to do it like this. It's already broken down for me. That dang yellow, what's going on with that? So let's see. It just wants to be a part of it, I guess. Okay. X equals, square root of 16 is 4. Square root of 4 is 2. X equals 8. Okay. Remember, if we had done it, x squared equals 64, and then take the square root, there it is. So either way, you're going to get the same answer. Okay, let's try this one. Y squared equals 20. Okay, again, we got to simplify. Notice those same numbers are going to come up because 4 is perfect square. So square root of 4 is 2. Square root of 5 is square root of 5. There's your simplified answer. X squared equals 36. X equals 6. 36 is a perfect square. We don't have to break it down. Uh-oh. All right. Okay. This one, there's only one thing to find, but we are going to take 6 times 6x squared. Remember, from algebra, 6x squared. 6x times x. And then 36 times 36. I'm not sure what that is, but I know they're perfect squares, so I'm going to just leave it alone for a while. I'll divide my 6 out before I take my square root. X squared equals, okay, this 6 will come out of this 136 6 times. So I got 36 times 6 left. Okay, I'm going to take my square root now. X squared equals square root of 36 is 6. Square root of 6. I'm done. Oops, that's x squared. Okay. So if you can kind of think ahead, then it'll help you. But, you could still get the same numbers if you actually multiplied 36 times 36 and then divided by 6. Just seems kind of a waste when you know you're going to take it out right away anyways. So think ahead. But that's how you use your corollaries. They're not hard, but again, you got to remember the words. Okay? Just keep saying them to yourself. All right? One more word problem. Okay, I'll go ahead and read that. You are preparing for a robotics competition. Okay, points A, B, and C. Here's A, here's B, here's C. Are located so that AB equals 20. There's A, B equals 20. Okay, AB is perpendicular, so we got that original right triangle set up. Point D is set up so that you have another perpendicular here. So this is that same look from this section. and DC is 9. You program the robot to move from A to D, okay, and pick up the plastic bottle. How far does the robot travel from? So clearly we're looking for X. All right, X is not a altitude or a leg, which is but the altitude's not involved because this is the altitude. It's not involved at all. So clearly we're looking for the leg. Let me just write the words. Leg is geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to that leg. Okay, so those are the words. Leg. The only leg we have is 20 inches. So I'm going to put 20 over here. Everything's in inches, so I don't have to worry about that. All right, hypotenuse would be 9 plus x, not 9 times x. And the segment, these are the two segments here and here. Adjacent to 20 would be x. Okay, so we get some multiplication. 20 times 20, 400, equals x times 9 plus x. And distribute 9x plus x squared. Okay, x squared, this is a quadratic with this x squared, so I'm going to pull everything over here because I want my 0, so I had to subtract 400. Now you can do the quadratic formula if you don't know the factors, but I happen to know that it's x plus 25 and x minus 16. So x is really going to be negative 25 or positive 16. Okay. I don't think x is going to be negative 25. Check it out. I don't think we can have a negative length. So x is really 16 inches. Okay. And again, if you wanted to do the quadratic formula, if you really, this would have been maybe tough to come up with, then remember a is negative 9. B is, I'm sorry, a is not negative 9. Good grief. A is 1. Hello, yellow lines, go away. A is 1. B is 9. And C, hello, is, oh my gosh, negative 400. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. Okay. 81 minus, oh my, what the heck? Just randomly, boy. Okay, well, I guess the yellow is there to stay. It's like a kindergartner here. Okay, negative 9 plus or minus 81 minus 4 times 400 is negative 1600. Getting worse here, over 2. All right, 9 plus or minus negative 9, 1681. Okay, 9 plus or minus, this has a square root, et cetera, et cetera, et cetera. You're going to get these same two answers. I'm not going to do it because this yellow is making me crazy. All right, so there's your answers. I'm sorry, homework. I want you to submit that by 10 o'clock p.m. and have a great day.